Okay, so the main objective of Lab 1 was to show an object moving at constant velocity and describe it by using Newton's second law. And we see that Newton's second law here is the final velocity vector is equal to the initial velocity vector plus the F net vector divided by mass times delta t. Now, because the object is at constant velocity, this means that this value, F final, or V final, must be equal to V initial. So this means that everything to the right of the plus sign must be equal to 0. We can assume that delta t won't be equal to 0 because that obviously the object is moving through time. We're viewing at it through time. It's not a still frame. There's things happening. It's moving through time. The mass can't be equal to 0, being A, because the object isn't weightless, and B, because dividing by 0 would create an undefined object, which is impossible. So the net force, must be equal to 0 here. Must be a vector of 0, 0, 0. This means that there are no surrounding objects acting upon our system, which is going to be a car, as I'll show momentarily, that will cause the object to change, speed up, slow down, brake, anything along those lines. So, we see through my video, I did choose a car because in this portion of a street in between two intersections, because I figured this would be a good spot to show where a car would have no need to accelerate, no need to decelerate. There's no objects in the road, anything that could block it, so it will move along a straight line at a constant velocity. And as we analyze our video through Tracker, we see that for the most part, it does move at a pretty straight line. We have a linear slope right here. It moves up all the way right to the point, and it has a pretty constant velocity. The changes in position are pretty much equal between each point. It does have a little bit of variance, but that could be a result of human error, like myself, right? 0.25, and I was a little bit higher than at 0.26. But thankfully for us, the y position doesn't really matter in this equation because we're only observing an object in 2D, one direction. So, as we take our value and plot it into our coding, we see that, well, after we do some analyzations and some editing of ourselves, I had to change the ball dot pause vector to be equal to the initial position, which is over here at 0.025, and I also had to find the velocity of the vector, which is found by using delta d over delta t, which would be the change of these two positions over the change in the time. So 0.298 minus 0.025 all over 0.034 minus 0 gives a value of 8.029 meters per second. So after keeping delta t at 0.01, because it's a small enough time increment where we can see a variable change, I also had to change the while loop. Now, because we're observing it through time, we had to find the final time of the object that we observed. So, scrolling down through Tracker, we see that our final time was at 1.3 seconds. And going back to our code, I had to change this back to 1.31 seconds. We also, as we discussed earlier, found that the F net vector is equal to 0, 0, 0. And then, using Newton's second law, we would find the position of the velocity vector, which is shown through here. Ball.vel plus F net divided by the ball.m times delta t. We also need the position vector, ball.pos equals ball.pos plus ball.vel times delta t. And as we run this through Tracker, or excuse me, not Tracker, VPython, and the ball moves pretty quickly, but we do get a linear line that is pretty much identical to what we see right here. It is a linear slope, it goes through a constant velocity, and it creates a line that almost looks identical. But to make sure that our model and our experiment data is both equal, we had to compare the two graphs by plotting them. And as we see as we plot them, the experimental position versus the model position over here, we see that they're not quite identical. The experiment position, which is of the car, versus the model position, which is VPython, is a little different. The experiment position was a little bit slower, so it didn't technically move at constant velocity. Now, this could be a result of many things. This could be my own error in plotting this points wrong, or more than likely, it is probably due to friction of the car. If the car was to coast through at a constant time, then we would see that without any changes in velocity, that it would for some reason slow down, and this is due to friction. Now, we do not count friction in this because we're assuming that the F net overall force is going to be equal to 0. So this leaves out the important part of this actually affecting the car. We say that there's no net force overall when there really is actually a net force. But even though we do say that net force is equal to 0, we do create a pretty much identical line between the model position and the experimental position that shows a pretty solid model of what we are looking at of an object at constant velocity.